My name is Baoning Wu. I'm a postdoc at Scripps Institutions of Oceanography at UCSD in the US. I'm going to switch gear to US a little bit. I'm going to talk about the 2024 magnitude 4.8 Tewksbury, New Jersey earthquake. This work is a collaboration with Fola and his postdoc Rashia Jalad at Lamont and my postdoc advisor Alice Gabriel. So let me change the pointer. So I'm sure many of you are aware of this, but just in case you don't, here's a map of US. All the dots are the file reports of earthquakes, of four earthquakes, they are in different colors. 2020, 2014 magnitude 6 earthquake in California, 2016 magnitude 5.8 earthquake in Oklahoma, 2011 5.8 earthquake in Virginia, and magnitude 4.1 earthquake in Delaware 2017. So these are file report. Basically, USGS collects a survey from people. If you feel the earthquake, you submit an online survey, which is called DigiFeel it, and they calculate in shaking intensity based on the report you submit. And so basically, you see that in eastern United States, these earthquakes are widely felt in a larger area compared to the Western United States. This is because earthquake in the eastern United States, they are, because this is a passive margin, it is tectonically more stable, so the seismic wave attenuation are weaker, so you can feel it in greater distance. So this result really highlight the differences between the ground motions in the passive margin in the tectonic active area, and this could be important because in passive margins earthquakes are rare, just like Hansa have mentioned. So, however, you need to often use the data you have in the tectonic active region to apply to the seismic hazard analysis in the passive margin. So there may be some issue in doing this, and this will be what we talk about today. All right. Today, I'm going to talk about a 2024 magnitude 4.8 earthquake in the New Jersey regions. This is earthquake in the largest earthquake in the New York regions since 1884. It is a oblique thrust event with a strike component. It was widely felt in the Northeast United States, and it provides a really valuable opportunity to study the ground motion patterns for moderate earthquakes in eastern United States. And one interesting fact about this earthquake is that it shows a stronger shaking towards the north-northeast and east-southeast directions. We know it because this area is densely populated, so there are many reported earthquake ground motions. So with some data simulations, we can see the pattern. And such a pattern cannot be explained by the empirical ground motion model, which is usually isotropic. And because this strong motion direction happened to be towarding the more populated area, so the community are really interested in explaining why this is the case. Many mechanisms have been proposed so far, like the source effect, which means the earthquake source causing these patterns, or path effect, such as basin structures and so forth, or side effect. For example, like probably there's a local sediment layer that amplify the ground motions. Today, I'm going to argue that it is this such pattern of north-northeast and east-southeast amplified motion is mainly caused by the source effects. So source effect has previously been proposed by Han et al. 2024. In this study, they used empirical Green's functions method to calculate how the earthquake ruptures. So basically, the earthquake start from the epicenters and propagate to northeast, to be precise, 55 degrees from the north. So they arguing that disruption directivity explain the ground motion amplification pattern. However, if you look at disruption directivity with the shake map, you see that actually there's still a mismatch between the amplified direction north-northeast and east-southeast with the rupture directivity uh, direction, which is highlighted by the red arrow. So I mean, it means that additional factor need to be considered. And in this study, we're going to argue that the additional factor is the radiation patterns, which is a result of the earthquake focal mechanisms. So to investigate that, we just theoretically calculated the S-wave radiation patterns because the strongest shaking is caused by S-wave. So we consider that by using the full space far field solutions, which should be good enough for this case. As you may know, S-wave radiation patterns will have a four lobe structures in 3D, and if you project it to the Earth surface, it will show a flower shape pattern. And here is calculated peak ground velocity using radiation patterns. So you can see that there are four lobes of amplified strong motion directions: north-northeast, east-southeast, south-southwest, and west-northwest. So these two directions, north-northeast and east-southeast, are consistent with what we observed. However, these two, west-northwest and south-southwest, is not what we observed. Of course, this is the case because we haven't considered the directivity. So the next step will be including the rupture directivity and see what's happened. So to do that, we just using the rupture directivity that is already obtained by Han et al. And then if we combining both the radiation pattern and rupture directivity, because the rupture is propagating to northeast, you will see the west-northwest lobe and south-southwest lobe will be shrinking, and the north-northeast lobe and the east-southeast lobe will be increasing. So to sum up, through this simple theoretical analysis, we can argue that in the observed data, we see north-northeast and east-southeast direction experience the strongest shaking, probably because of two reasons. First, these two directions are within the major amplification lobe of the S-ray radiation patterns, which is coming from the oblique focal mechanisms. And second, these two directions align with the rupture directivity direction, which is 55 degrees from the north, causing additional amplifications. We can test it with each data point. So we tested with two data sets. One is the actual seismic record at different stations. So here in the map, I show you the P ground velocity record of all the station within 5 degrees of the epicenters. So visually, you can sort of see and amplify directions in the north-northeast. However, you can see the decay of PGV with distance, which make it hard to analyze the amplifications directions. So to do that, you need to first remove the trend of PGV decay with distance. So you can do that by first.
You're now at 10 minutes, just so you know.
Okay, great. Thanks, Paula. So you can do this by feeding having a best fit decay trend, and then normalize each data point with this mean trend. And on the left-hand side is a rows diagram. Each dot is one data point, and this black are the median amplification factors in a 30-degree moving beam. So to interpret this, if this direction have value bigger than 1, it means that ground motion is amplified. If it is smaller than 1, it means it is de-amplified. So you see that the north-northeast and east-southeast have amplified ground motions. And also this direction also have some amplified ground motions. You can now we just calculate theoretical ground motions, PGV at all the stations again. And then we can do the same Rose diagram analysis. You can see that first, I think the first feature I see is that the amplified directions is captured by the theoretical model. However, because our model is really simple, the amplitude of the amplifications are overestimated. However, we feel happy that we can capture the directions of ground motion amplifications. Again, you can do the same thing with another data set, which is the file report data set. For the time's sake, I will skip the details, but basically you just calculate the ground motions. You can see the observed data is very messy, while the synthetic data is really clean. However, if you just calculate the median of the application factors, you can see that the observed data show north-northeast and east-southeast amplification direction really strongly, I guess really clearly, and this is captured by our theoretical model. So this is like other people propose that side effects is the reasons that you have these amplifications directions. We don't think that is the case because we use the USGS VS30 model and NGA's ground motion model to calculate the PGV. This is a standard hazard analysis product, and you don't see amplifications direction in the north-northeast and east-southeast. And as Fowler told me from the very beginning, New York is built on bedrock, so you shouldn't see strong side effects here. All right, so this to quickly summarize, the north-northeast and east-southeast direction experience stronger shakings in the in the Tewksbury, New Jersey earthquake because first, they lie within the major amplification lobe of the S-wave radiation pattern, and second, they are closely aligned with the rupture directivity. Although our simple model captured the directions of amplifications, it overestimated contrast, indicating that additional source complexity and 3D velocity structures are needed to fully reproduce the observed ground motion characteristics. Nevertheless, we think that in the tectonic stable regions, rupture kinematics and radiation patterns might be better preserved due to the weak crustal attenuation in this area, and this usually is not in the seismic hazard practice. So therefore, we think that accounting for these source effects may be crucial for improving seismic hazard assessments in the tectonically stable regions, including the New York regions. All right, that's so much for my talk, and we'll welcome questions and comments. Thank you.
Thank you, Baoning. We now welcome questions for Baoning. Sasha, please go ahead.
It's me again. So I was wondering whether you could speculate a bit on the stress field, on the driving forces, on the actual underlying geodynamics that have been causing this earthquake.
Let me get this pen out. Yeah, I'm not an expert on this, but and Fowler is, and so I'm quoting Fowler. I think this area, all the stresses are coming from the. Okay, how do I move that? I think this is a leftover stress with transpression stress regime, but I'm not fully sure whether that's the case. We have several historical earthquakes in this region that have focal mechanisms that all show like oblique structures, oblique sleep kinematics with thrust and strike sleep. So that seems to be a common tidal earthquake in this region, reflecting the leftover stress from the rifting beforehand. But this is my guess. For I can follow up. So yeah, I don't know whether that answer your questions.
Yeah, partly, but it opens another question because could you separate the earthquakes that you see here out into those that are affected by these inherited faults and maybe others that are affected by something else? Because the trend of the Tewksbury earthquake and then the ones further to the west is the same, but the ones that are further to the east is not the same. What is the structural differences in these regions?
Yeah, I think that could be. I just don't think we have enough data to say anything that is conclusive, because that's where you can't do a proper stress inversion in this area, I guess. You have to base on geology to make a guess. And this earthquake, this 125, those earthquakes are quite small. They may be strongly affected by local stress heterogeneity, while this earthquake, Tewksbury and 3 and 4, they are larger. I don't know whether. Yeah, I think the short answer is I don't know. I don't have answers.
That's fine.
So
That's fine. Thank you.
I'm just speculating. But Fola is here, is the most knowledgeable people about this area. So
Yeah, I'm not sure he's allowed to answer.
No, I'm not. I'm not allowed to.
yeah. If he don't have an answer, then I don't have an answer. I still don't know hints. Yeah. But thank you for the
Thank you.
question.